Hello guys, good morning to all of you. Welcome to another session. Just a moment. Can you hear me? Today we'll be discussing the second part of OPAMP, operational amplifier and their applications. And we gave you a homework. Have you tried this? In the OPAMP circuit shown in the figure below, the input voltage is 1 volt. The value of the output voltage is. Good morning, Vantage. Did you solve this problem? This came in June 2012. Look, in this OPAMP circuit, if you closely look at, input voltage is 1 volt, that is okay. Input resistance 1 kilo ohm, this feedback resistance 1 kilo ohm. Now this V0, you have to find out this output value V0. Now you can see V0 is here, so you can imagine it here also, here also. And as this OPAMP has infinite input impedance, no, ideal OPAMP has infinite input impedance. What does it mean? The current will flow via this path. Okay, so what will be the value of the output V0? So at this position you will get a virtual ground because of this negative feedback from this resistance. We will have a virtual ground here. Virtual ground means the voltage of this point will be 0 volt, right? So if you apply KCL, then as per KCL, I have already provided you the notes for KCL. As per KCL, if you consider a node or a junction, then the total current input will be equals to the total current output. Total amount of current input is equals to total amount of current output. Now you see, as this is in series connection, so same current I will be flowing through it. Here also I, here also I. What is the value of I? If you calculate the voltage difference and you divide by the resistance, V is equals to IR formula. From that you can get the value of I. Okay. So let us do this. For this path, actually we are applying KCL. So 1 minus 0 by 1, 1 minus 0 by 1, this is equals to 0 minus V0 by 1. So what is V0? V0 is equals to minus 1 volt. Option C. Clear? If anyone has any question, you can ask. Now, if there is no question, we can move forward. There is something called adder or summing amplifier. Let's talk about that. How can we add voltages using an OPAMP? So this is known as adder or summing amplifier. Okay, let's say we have an OPAMP like this, negative, positive. While studying this OPAMP, we generally use this symbol, negative upside, positive downside. But in question or anywhere else also, you can see the opposite scenario. They intentionally can invert this. Positive side they can give up, negative side they can give down. So you have to be very careful. Okay. So it is actually an inverting amplifier. This is RF, let's say, and in the inverting part you are applying various inputs. Okay, let's say you have various potentials, voltage sources V1, V2, V3, let's say n number of voltages you have, and they are connected by some input resistance like this, R1, 2, R3, so on. Let's say this is Rn, and they are connected to each other. In this way, and is further connected to this. So what has been done? In the inverting amplifier, we had only one resistance, but here multiple resistances and voltage sources. So you see V1 R1, so current I1 will flow through this path, current I2 will flow through this path, current I3 will flow through the path and continuously up to current IN will flow through this. Their sum will be there, that will make the total current I. Again, that I will also flow this feedback resistor. So can you calculate V0? This will act as a summing amplifier. Good morning, Harry. Ajay, Murli, where are they? Look, one thing you can see from here, that the sum of currents I1, I2, I3, IN, their sum is I1, I2, I3, IN equals to I. So if you apply Ohm's law, V is equals to IR formula, I is equals to V by R. Look, this is at this is at zero potential. So this point will be at the virtual ground, because this is joined by feedback resistance. So this will act as a virtual ground. What does it mean? The potential of this point will be 0 volt. Okay. So V1 is the potential here, 0 volt is here. So V1 minus 0 by R1. Okay. So V1 minus 0 by R1, that will be your I1. In the same manner, I2, V2 minus 0 by R2. I3 will be V3 minus 0 by R3, and so on will be Vn minus 0 by Rn. This will be equals to I. And from this, what we can write? What is I? I on the other side, you can see the same I is flowing through this. Here also I is flowing. So I is equals to 0 minus V0 by Rf. 0 minus V0 by Rf, using the same Ohm's law. So from this we can write the value of V0 is equals to, this negative sign will be there, times Rf will be multiplied with all the resistances. So it is Rf by R1 times V1 plus Rf by R2 times V2 plus Rf by R3 times V3, and so on, Rf by Rn times here. Can you write it? गुड मॉर्निंग अजय मुरली, आप लोगों का ही तो इंतजार था। Now in this scenario, if you make all these resistances equal, what I mean, if you make R1, R2, R3, all of them equal to be, let's say one resistance R1, okay, then what you can write, V0 is equals to minus RF by R1 times V1 plus V2 plus V3 and so on up to. So what does it signify? It signifies that the output voltage is nothing but the sum of the voltage with some multiplication factor, with some scaling factor, you can say. So if you choose the resistances in such a way that RF and RF and R1 are same, then they will cancel, they will become 1, and you can easily get the summing of the voltages. This is your adder or summing amplifier. Understood? Any question? Now, how you can subtract voltages? If you are given two voltages, for adding there may be multiple voltages, but if you want to subtract, then there will be only two, right? So that is known as a differential amplifier. You will amplify the difference. Okay. Look at it. Once again, this OPAMP will give you the feel of benzene, okay, every time you need to draw it. We have one voltage source, let's say V1, connected with some input resistance, let's say R1. Another voltage source we have V2. Let's say that is connected by R2. Okay. Let's take it R1 as well. This is R2. And the twist is here another resistance, that is R2. From here you are taking the output. Okay. Let's do reverse thing, okay. I am placing V2 above V1 below. Okay. Now this is connected by some feedback resistance, so there will be virtual short. Look, virtual ground and virtual short. Virtual ground one time you are using, another time you are using virtual short. Did you get the difference between these two? When zero potential is there on the non-inverting terminal and feedback resistance is there, then we have virtual ground. But if the voltage is other than 0 volt, then we will have virtual short. Clear now? So here we will get the scenario of virtual short. So because of this, if I consider that this point is A, this point is B, because of the virtual short property, voltage at A will be equals to voltage at B. Okay. So you see what will be the current through this path. Whatever current it will flow, same current will be flowing through this feedback resistor. So again we can write V2 minus VA by R1 is equals to VA minus V0 divided by R2. Let's say this is equation number 1. On the other hand, you can see the current is flowing in this path, you can say, right? So V1 minus VB by R1 is equals to VB minus, this is 0 divided by R2. Look, because of the infinite input impedance, current is not going in this path. Current is going along this path. And we could write this relation. Let's say this is equation number 2. Now, because of the virtual short, okay, let's name these points. This point is A, this point is B. Because of the virtual short, okay, let me just redefine this line. Because there is feedback resistor connected to the inverting input, the points A and B as shown in the figure will be in a virtual short condition. Sounds good? Therefore, voltage at A will be equals to voltage at B. Now, if you subtract equation 1 from equation 2 from equation 1, what you get? VA and VB are same. So, you will get V2 minus V1 divided by R1 equals to minus V0 by R2. That makes it V0 equals to R2 by R1. Because of the negative sign, V2 minus V1 will become V1 minus And hence we can write therefore the circuit amplifies the difference of the two input signals. Clear? Try to notice one thing. This is a very important observation. If you can see, can you calculate VB? This can be done in other ways also. If you can evaluate the voltage at B, means VB, where you can evaluate, then you can directly write the voltage of this point A as VB. Then you can just use one relation and you will get the desired output. Now, how can you calculate VB? You can calculate it from equation 2. We have already told you how to calculate it, but let me just show you once again, because this particular thing will be used many times. You will get to see. So you don't need to write all the things. What you will do, let's say, you want to calculate the voltage at V2, VB. So what you will do, VB will be equals to, look, V1 by R1 R2 are in series, R1 plus R2. This is the current. V is equals to I into R. Across which resistance you are taking this voltage? Across R2, you have to multiply it with R. Okay, this is the formula you can say. Now, to cross verify, you can do this thing. Actually, we have done that. V1 minus VB by R1 is equals to VB minus 0 by R2. Okay. So, what we have, VB, if you take common, we have 1 by R1 plus 1 by R2 is equals to V1 by R1. Okay. Therefore, VB into R2 plus R1 by R1 R2 times V1 by R1. R1, this R1 getting cancelled. So we have ultimately VB is equals to V1 by R1 plus R2 multiplied by R2. So ultimately, we got the same result, right? So actually, we have applied this. This is what you can say we have applied KCL at this node point. Current, total current entering into this node equals to total current leaving. Okay, we have shared the PDF for KVL, KCL, and all the other network theorems. You can check that. So using that, we are getting the same result. So you can you don't need to calculate this much. You will just see. You have to calculate the voltage against this R2. So V1 by the total resistance into the resistance. V is equals to IR formula. Is this trick clear? Tell me guys quickly. Murli, Ajay, Harry, Vantage. Hello, let's solve a problem. In the operational amplifier circuit below, the voltage at point A. Look, one thing I would like to tell you here. Let's say if you have, let's say there is no feedback resistance. In that scenario, if you have any input voltage. So gain is infinite, right? Open loop gain for an open is infinite. So will you get infinite voltage at the output? Remember one thing, in operational amplifier, the output voltage will not be greater than the supply voltage. Here, 4 and 7, we have the supply voltage at 4 and 7 equal plus 5 minus 5. So whatever voltage will be here, that will be the maximum voltage you can achieve from the output. Remember this one thing. Now, otherwise, you imagine if it was like the theoretical, you would spend only a small amount of voltage and you will get enormous, infinite amount of amplification. That is not there. You will not get more than the supply voltage. Did you get this point? Okay, look at this problem. In the operational amplifier circuit below, the voltage at point A is. बताइए दोस्तों क्या होगा आंसर? What will be the answer of this question? Let's see how much you have understood. Look, the question from electronics will come in this way. You do not need longer calculation. If you know you have the concept, you can do it in few seconds also sometimes. So that is why these electronics questions are game changer. Many students, what they have, they are good at electronics. Then they solve all the questions from electronics. Maybe 20 to 25 marks they just score from the electronics. In that way, their score boosts larger amount. Option C, 0 volt. How 0 volt? And what about the 1 volt? 1 volt will not affect. Voltage here, voltage here, voltage. If there is no current flow through this resistance, will there be any drop? A resistor will do its job only when you are trying to send current through it. Only when current is flowing through it, then only resistance will do its job. Otherwise, this 1 volt will be reflected here. No? The input impedance of this op-amp is infinite, right? No current is entering into the op-amp. If there is no current entering into the op-amp, means there is no current flow. So this 1 voltage will be reflected here, and there is no feedback connection, so there is no point of virtual short. So 1 volt. Input impedance is high. So there will be no input current. Hence, the voltage of A will be 1 volt. Clear? Instead of one resistance, if there are multiple resistors, then also it will be, the answer would have been 1 volt. You can think it in this way: because of this infinite input impedance, the circuit is not able to complete. If the circuit is not completed, there will be no current flow. If there is no current flow, there will be no drop. 1 volt will be reflected at A. I think it is crystal clear to everyone. After this, we will be discussing about two very important circuit. One is the integrator circuit, another one is the differentiator circuit. Okay, integrator circuit will integrate, differentiator circuit will differentiate. So let's talk about them. Firstly, we'll be talking about integrator. How to design an integrator using OPAMP. So the basic structure of this OPAMP integrator looks like this. Look, whatever basic operation you require, you have already learned. Now, whatever things we will be discussing next, that will be just their applications, or you can say extended version. If you replace the feedback resistor by a capacitor, it will behave like an integrator. Okay. Now, this is the circuit of an integrator, and you can see there is a capacitor. Now, whatever is there, because of this feedback, this is a feedback impedance, there will be a virtual ground at this point. And current through this resistance I, current through this path will be equals to current through this path, because of the KCL. Current entering into the junction is equals to current leaving the junction. So you can apply KCL here, and you can write current I is equals to Vs minus 0 by R. Okay. So current I is equals to Vs minus 0 by R. Can I write it? I, because you have C, you need to write C in such a way that you can correlate with I. I is equals to dq by dt, rate of flow of charge. Now, because we do not know a relationship the way we know a relationship for voltage, so we have to express the relationship in such a way that we can put the value of C. So I is same, so I is dq dt. Okay, let's do another thing. This is one relation we have. I for this path. For this path, we can say I is equals to dq by dt is equals to d dt of q is equals to CV. C into voltage difference 0 minus P. So you are getting minus C into dV0 by dt. Okay, where Q is equals to C into 0 minus V0 is the instantaneous charge on the capacitor. Clear? So from this, can you calculate V0? Therefore, we have Vs by R is equals to minus C times dV0 by dt. Okay. And hence, we have dV0 by dt is equals to minus 1 upon RC times Vs. Vs may be a sinusoidal signal, or maybe a square signal, or maybe a triangular signal, whatever input signal we have. Vs is the input signal, input voltage. So from this, we can write V0 is equals to minus 1 upon RC. RC is a constant, integration Vs dt plus some constant A. Okay. So this will behave as an integral. So if you let's say if you have an if you have a signal like this, square wave signal, let's say, if roughly I am just telling you that this is your Vs. Now if you pass it through an integrator, what kind of curve you will get? Tell me. Will you not get a triangular type thing? Look, if you put Vs is equals to 0, then it is 0. And from here to here, let's say, if you start from here, okay, so let's say t is equals to 1 to 2. You have some constant value into t. So it will be like a triangular wave, right? It will become a triangular wave. Because of this negative sign, you can get the slope in the opposite side. Okay. So this kind of signal you can expect. Check it whether I'm drawing it. Do you agree with it or not? I need to check it by saying it will be a little flat, as you see. When it is maintaining between 1 and 2, when it is maintaining, then that will, you have to just check it, okay? Now this is the ideal integrator. Now in practical integrator, some additional component is added. This is our ideal integrator, the basic circuit you can say. And it need some modification. In the practical circuit, when you want to use the practical circuit, you need some modification. In the practical circuit, what is done? A resistance is added here. Okay. R1, and another resistance is added in parallel to the capacitor in this way. This is your practical circuit. So generally you see the basic circuit, okay? This is just for your information. The practical circuit you don't generally see. Now why this R1 is added? The value of R1 is equals to, it is chosen in such a way that it is the equivalent of R1 R2, R parallel R2 is added to minimize the error due to offset. We have already talked about offset in the last class. Now R2 is chosen in such a way that it is much greater than 1 upon omega c, where omega is the angular frequency of the input signal. And it is added to avoid the problem of DC stability. Okay, you just know it for your information. Otherwise, the main circuit is this. The main formula is V naught is equals to minus 1 by RC integration of ES dt plus K. Let me know if you have any question. Your comments came. I could not see your comments before. It was. Now I can see. Ajay Murli. R parallel R2 means. Okay. R parallel R2 means the parallel resistance of R and R2. Like if you have, let's say, I'm writing for an example, R is equals to R1 parallel R2. What does it mean? Is R1 R2 by R1 plus R2 na? Is like making 1 by R, 1 by R1 plus 1 by R2. This is the meaning of this equation is written as R is equals to R1 parallel R2. Got it, Murli? So once this integrator circuit is done, let's go to the differentiator. In differentiator, the only difference will come. You see, the capacitor was connected to the feedback resistor. In place of the feedback resistor, the capacitor was connected in case of an integrator. In case of a differentiator, this capacitor will be connected here at the input resistance. Okay, and here will be a resistance, another resistance. Resistance in parallel, yes. R parallel R2. So the equivalent resistance when you connect R and R2 in parallel. If you can also write it. This means the equivalent resistance when R and R2 are connected in parallel. Okay, crystal clear. Let's go to the differentiator circuit. Look, in this integrated circuit, if you consider, look, we have considered only positive half cycle, the negative cycle and half cycle is missing here. But if you consider the negative half cycle also, this will give you a full triangle. It is not forming triangle. So you have understood this one, right? Now I am giving a homework. As a homework, you take this as a homework. You will try to plot same thing, but little different. Same but different. Okay. सेम बट डिफरेंट चीज आपको करना है. Okay, take this as homework. If I make the 0 point here, previously this was supposed to be 0, right? Now if we consider this to be the 0 line, we will have, you are having positive half cycle here, negative half cycle. Okay, let's say this is K, this is minus K. So what changes will be there in this curve? Look, because of the negative sign in the output, whatever curve you expect, that will be on the other side, right? So you are expecting a triangle along this, but you draw it in this way because of this negative sign. I hope this is clear. Let's talk about differentiator. As I told you, in differentiator circuit, what will be the difference? The capacitance will come at the place of the input resistance, and the feedback resistor will remain as it is. This is the basic circuit. V naught, this is R, this is C, this is the input voltage Vs. Basic circuit is the one you need to tackle with in the examination. They will not give you the practical circuit. Intentionally they can give, but mostly you can use the formula of the basic circuit. So as usual, current entering is equals to current leaving. I current is flowing through it, I current is flowing through. So what is I here? I, dq by dt. We are writing it for this path. This is equals to d dt. Q is equals to C into difference in voltage. Here it is Vs, and because of this virtual ground, here will be 0 volt. Okay, C times Vs minus right, and again here I is equals to 0 minus V0 by R, and we can write since both i's are same, d dt of Vs is equals to minus V naught by R, and that makes V naught is equals to minus R C is a constant dVs by dt. As you can see, you get the differentiator formula. So this OPAMP is giving an output which is the differentiation of the input voltage. That is why this is working as a differentiator. In the previous case also, the output voltage of this OPAMP is giving an output in such a way that it is integrating the input voltage. That is why it is acting as an integrated circuit. Understood? So this is the main formula. It is quite easy to remember it, right? Remember one thing, that as it is an inverting amplifier, okay, inverting amplifier, you can say inverting input is given to the inverting input. So there will be negative sum always. Some multiplicative constant for integrated is minus 1 by RC. Here it is 1, here it is only RC. Okay. And when we are considering integrated, you have to integrate. When you are considering a differentiator, you have to differentiate. Okay. This is what it is. For an example, if your input signal Vs is equals to, let's say, a sinusoidal signal V0 sin omega t, what will be the output? The output V0 will be minus RC omega RC V0 omega cos omega t, right? This will be the output voltage. Now this is the basic circuit. What changes will be there in the practical circuit? Look, I'm just omitting these things, but I need to be very careful while omitting things. What we have in the practical circuit, a resistance is connected in series with this and at this place. We have Vs here and a resistance R1 connected here and another resistance R is connected here. So this is your practical differentiator circuit. This is circuit of a differentiator. Okay, same value of resistance is connected here, so it is not an issue. R1 is connected because there is an issue of high frequency gain with this circuit, so that make the circuit unstable. That is why this Rn is connected, and its value is almost 1/10 of this to, let's say, 1/100 of this. A small resistance connected here. So you can just note few things here. The differentiator, the basic differentiator circuit has high gain at high frequencies and thus it amplifies high frequency noise. Sorry. And switching spikes. The circuit is found to be very unstable. In this situation, can be avoided by connecting a resistor R1 in series with C. The value of R1 is usually of the order of R by 10 to R by 100. Now what does this R1 does? What does this R1 do? The resistor R1 limits the high frequency gain. And makes the practical differentiator useful only for frequencies below the limiting frequency given by 1 upon 2 pi e. For the practical differentiator, the maximum frequency allowed will be 1 by 2 pi CSIR. So feedback is always given by a register. Why? Phase difference is the reason. Yes, if you give register, then the phase difference will be pi. Pi phase difference means a negative sign will be appearing. If you use instead of register, if you use another thing, then you can have the register the phase difference. We have already done using Z1 and Z2. That was a general case. Okay, so the phase difference will be changed. If you just want to invert the phase 180-degree phase shift, then you can use the register. If you want other type of phase shift, then you can use accordingly register or anything. And another reason is that if you are dealing with DC signal, DC signal can be passed through register, but DC signal will be blocked if you want to pass it through capacitor. That is the reason also capacitor is not used. Actually this is the main reason. Phase shift is the additional thing. Because in case of integrator circuit, you see it will integrate. If you use, look, you can use multiple things. If you use resistor, it will act as an amplifier. If you use capacitor, it will act as a integrator. Okay, and you will see if you replace that feedback resistor with a diode, let's say, then it will do another job. We'll talk about it. What will happen if you replace the resistor by a diode? This is the problem we have. In the OPAMPS circuit shown below, a sinusoidal signal of frequency 10 Hz and Vj is the output signal. Magnitude of the gain and phase shift respectively close to it. So your your question, Harry, your query has been given in the form of a question. Now you see a combination of resistor and capacitor. What you do if you have both? Then simple. You have to take up the approach. It is like Z1 and equivalent impedance you can calculate. You can imagine like Z1 is here and you have to find out the equivalent impedance, then make it to Z2. Can you do this? Interesting problem, December 2012. Give it a try a little bit. The way I told you, Z1 and Z2 calculate. Z1 is 1 kilo, that is given. Z2 you need to calculate the parallel combination of capacitor and a resistor. So you can write the equivalent resistance of a capacitor 1 by j omega c, and resistance is R. They are connected in parallel, so you have to use the parallel formula R1 R2 by R1 plus R2, where R1 is 1 by j omega c. Okay. Look, what did I tell you? We need to consider a circuit like this. Vi, instead of this resistor, let's say we have some impedance Z1. Negative, positive. Let's say we have Z2 here. So this is an inverting op-amp. The virtual ground is here. So for this is an inverting amplifier, you can say. So what will be the gain? You have to find out the magnitude of the gain. The gain AV is equals to V0 by Vi. Now how much? Minus R2 by R1, so Z2 by Z1. Right? This is the gain. Can you write it? So you have to find out the magnitude of this, because AV will come out to be complex quantity because we have capacitors. What is Z1 here? Z1 is equals to this resistance of 1 kilo ohm. What is Z2 here? Z2 is the equivalent resistance of the 10 kilo ohm resistance and that capacitance of 0.01 microfarad. Okay. So let's name this capacitance as R2 and the capacitor to be C, and for the time let's name it R1. So it is Z2 is like, instead of writing this is inconvenient to write, R parallel C2 or C, R2 parallel C. Okay. C is the capacitance. We need to give reactance here. So it is not C, it is 1 by j omega, because the reactance of C is 1 upon j omega C. Understood? Now, what is the R1 R2 by R1 plus R2? We are using that formula. So R2 by 1 by j omega C divided by R2 plus 1 upon j omega C. Note, equivalent resistance of R1 R2 is R1 R2 by R1 plus R2. We have just used this. So this is equals to how much? R2 divided by j omega CR2 plus 1. So gain is equals to minus Z2 by Z1. Z2 is this R2 divided by 1 plus j omega CR2. Can I write it? In the question, you have been given frequency f. We have calculated in terms of omega. What is omega? Omega is equals to 2 pi f. And R1 is 1 kilo ohm, so that is cancelled. Okay, so no issue in this. So R2 by 1 plus J into omega is equals to 2 pi f, and this CR2 will remain. Right? So what will be the magnitude? If we have this complex quantity, what is the magnitude? Magnitude of AB means the negative sign is absorbed. Magnitude of R2 is R2. Okay, the real thing. And magnitude of 1 plus J into 2 pi FC R2. So magnitude of R2 is R2. Magnitude of 1 plus J 2 pi FC R2. This is root over 1 plus 4 pi square f square c square R2 square. Can you write it? Here we have used, let's say you have a complex quantity z is equals to x plus iy. What is the modulus of z? Root over x square plus y. Same thing. Okay. J is square root of minus 1. J is I here. So put the value of R2. R2 is 10 kilo ohm divided by 1 plus 4 pi square. 4. Look, we are using in kilo ohm. Okay. Kilo ohm, R1 was also kilo ohm. So kilo ohm get cancelled. Pi square. Pi square is 3.14 square. F is 10 hertz given to you, 10 kilohertz or 10 hertz. 10 kilohertz होगा, 10 hertz. C is 0.01 capacitor, 0.01 microfarad, 0.01 10 to the power minus 6. Into R2. R2 is 10 का square. As a 10 kilo ohm in here. 10 into 10 to the power 3 square. Look, don't confused here. R2 by R1 was there. So 1 kilo ohm, that kilo ohm. Okay, if it is making the confusion, let's just give R1. Okay. You may think that once you are using 10 for R2, another time you are using 10 kilo ohm for R2. So the actual reason is, for when I am putting it here, R2 by R1, 10 kilo ohm by 1 kilo ohm, that is 10. Okay. And here we have just put 10 kilo ohm. Is this confusion clear? Or you did not just notice this? Tell me, what magnitude are you getting? I'm not getting my calculator. Mr. Calculator, where are you? So you can see how many things we need to keep in mind while doing a calculation. If you are little bit okay, if you are little bit off the track, you can do grave mistakes. You see, this part is almost negligible. So square root of 1 plus this is approximately 1. So 10 by 1 is 10. The magnitude is coming approximately 10. So once you get the magnitude, what is the phase? Phase equals to pi minus tan inverse 2 pi FCR2. Okay, now we have already done it. This phase information in one of the derivation in the last class. Okay. Look, this 2 pi FCR2 very small number. So tan 0 formula, tan 0 is 0. So this part is 0. That is why it is pi. The correct answer for this question is answer D. Tell me how interesting this question was. In which year it came? December 2012. Look, once you get the basic understanding, you can answer many big complicated questions. आगे बढ़े दोस्तों, and we move forward. Let's talk about logarithmic amplifier. Logarithmic amplifier. What we have in this logarithmic amplifier? In the logarithmic amplifier, the feedback register is replaced by a diode. Negative, positive. V0 to V1. Positive, negative. This is the logarithmic amplifier. So from node analysis, we can say total current entering is equals to total current leaving. How much voltage will be dropped here? That will be VF, forward bias. Okay, forward current. Sorry, forward current. Diode flows the current in one direction. current will be flowing it, and the current you will be having the voltage, corresponding voltage here. Now how we are getting it in a logarithm? What is I? Current I flowing through this resistor, sorry, diode. I is equals to, you know, Is exponential E Vf divided by eta kt minus 1. Is exponential Vf EVF by eta kt minus Is. Now if we consider that E times Vf by eta kt is much greater than 1, then I is much greater than Is. Okay, it is much greater than 1. This term I we can approximate to Is exponential EVF by eta kt. Can you do this? Now this point is virtual ground, so the voltage is here 0 volt, and again I is equals to V1 minus 0 by, let's say this resistance is R1. Okay, we can say that V1 by R1 is equals to Is exponential EVF by eta kt. Simple. Now can you tell me what is this Vf? What is this Vf? You can imagine something like this. This is V0, this is Vf. If I apply this a KVL, positive to negative, negative, positive to negative, negative, so Vf is nothing but minus V0. So V1 by Is R1 is equals to exponential minus E V0 by eta kt. If we take logarithm on both sides, V naught, you will get minus eta kt by E ln E1 by Is. You can see the output is the logarithm of this input voltage. So that is why this OPAMPS circuit acts as a logarithmic amplifier. Any question you have? Voltage across the diode, yes. Tell me guys if you have any question or query. Otherwise, we can go for the next problem. Okay, let's go to the next problem. Where is the next problem? Too many pages I have kept blank. If the parameters y and x are related by y is equals to log x, then the circuit that can be used to produce an output voltage V0 varying linearly with x each. Read the question and do it. This is actually a mathematical question. If the parameters y and x are related by y is equals to log x, then the circuit that can be used to produce an output voltage V0 varying linearly with x each. First circuit is the integrator circuit, right? Integrator. It will just integrate y dt minus 1 by RC. It will be something like this. That's some constant. So, is it varying linearly with x? No. It is not varying linearly with x. Option B. Here, what will be the V0? It will be, let's say I'm just writing proportional to logarithm of y. We have seen it. ln of V1, you can say ln of y. V0, it should be varying as linearly with x. Okay, V0 should be varying linearly with x. Okay, and y is log x. Y is log x. If I, instead of taking ln y, we can take log y. So actually this becomes log of y is equals to log x. Log x. It is not what it is. This is the logarithmic amplifier. Logarithmic amplifier. This will be the answer, but let's talk about the last one. Yeah, this is the differentiator. This will differentiate. Differentiator means what will be its output? Its output will be minus RC integration dy by dt plus some constant. Let's say k. or if you just remove this constant, this is not working again. But let's look for option C. Option C will be the correct option. It is remaining. You see, this is an anti-log circuit. Anti-log. Here output voltage V0 will be proportional to e to the power y. Okay. E to the power log x. So this is x. So V0 is proportional to logarithmic amplifier we have done. So in your examination, look, anti-logarithm circuit has been given. So let's try to derive this. Anti-log amplifier. So you get the picture. We have some diode here at the place of the input register. At the inverting input, we have negative, positive output, and it is connected via feedback resistor R. This is the diode. It's a VI we have. So this will be at the virtual ground. Once again, we will have EF here. Same current. Here, how much is the current flowing? ID, diode current, right? And same current should be flowing through this also. Okay, here also you should be same amount of current. Let's not denote it. Let's denote it by I. I and ID are same. So what is ID? I through diode. You can approximately write it as equals to IS exponential E VF by given I is equals to, this is 0 volt, 0 minus V0 by R. So since same current flows through the diode and the feedback resistor, we can write I is equals to ID means V0 by R equals to IS exponential VF by. So from this we get V0 is equals to minus IS into R exponential eta kt by E. It has a special name. Do you remember? VF by what is this term? Kt by E. Sorry, eta, not eta kt, kt by E. We have already introduced this thing. Kt by E. So this is what? Voltage equivalent temperature. It is represented by Vt. You remember 0.026 volt. Eta Vt we can write. So this is anti-log. It is proportional to V0. Output voltage is proportional to exponential of F. Acha, okay, let's do a little bit of more calculation, because Vf is nothing. We need to express it in terms of Vi, right? Now, once again, you take the case of Vi. Okay, here we have something like this. We have Vi, positive, negative. This is Vf. You go it in this direction, negative to positive, positive, positive to negative. So Vf is equals to Vi. So we can just replace it now. Minus Is into R exponential Vi by eta Vt. Vt is the volt equivalent temperature, or you can say yes, it is proportional to exponential of the input voltage. This is the anti-log circuit output. Is it clear like crystal, guys? Tell me. One last problem we have to do today and we'll conclude the session. The last one is the most complicated problem. Look, the last problem which we are going to do is a difficult problem, very difficult problem. This kind of problem may not, it may come, actually it came in part C. Okay, generally this much of lengthy question does not come, but let me show you the question here. A time varying signal Bin is fed to an open circuit with output signal V0. The circuit implements it. So it's a combination of two concepts, filter and OPAMP. OPAMP, using OPAMP, filter has been designed. High pass filter, low pass filter. You know the concept of high pass and low pass. Low pass filter, actually it passes only the low frequency signals. High pass filter, it passes the high frequency signal, the low. This is your low pass filter. This is high pass filter. Okay now. So let's say frequency versus gain. So as you can see, there is a cutoff. There is a cutoff. Beyond this, all the signal will be blocked. Beyond this, below this, all the frequency will be blocked. This is the concept of high pass and low pass filter. Now, can you do this question? Or do you want to try it at home? Tell me. Okay, we have to draw this. Okay, so you see we have multiple points here. Let's call this point to be point A, this is B. Okay, so because of this feedback circuit, voltage at A and B will be same. Another point we have here, let's say C. Let's say this point is T, and here let's imagine the voltage is E. Okay, now as per KCL, total sum of currents entering into a junction is 0. Okay, current entering is positive, current leaving is negative. The sum of I is equals to 0. This is the KCL. So we are applying KCL at node A, let's say. Okay, look, we need to calculate the gain V0 by Vi, but the problem is Vi is given to the non-inverting terminal and it contains too many circuitry. So we need to simplify this circuitry to get V0 by Vi. Okay, so we are applying the KCL at node A. So what will be the result? Look, you can do Vn minus Vin minus Va, Vin minus Va divided by 1 kilo ohm equals to Va minus V by 10 kilo ohm. Can you write? It means if I take, let's say, Va common, so it is 1 plus 1 by 10. Remember, we have put resistance in kilo ohm. Okay, we'll tackle it at the end. This is equals to V in plus E by 10. This is equals to 11 by 10 Va is equals to V in plus V by 10. Let's name this equation 1. No issue till now, going smooth. What is unknown to us? We do not know V. So we need to first calculate V. Then once V is evaluated, we can calculate Va, right? So to calculate V, we are applying KCL once again at point B. If you apply KCL at point B, what you get? KCL at node B. So here, as you can see, because of the virtual ground concept, virtual short concept, V at B is equals to V at A. Step 2, this one. We have just taken Va common, no? Va 1 by 10, and this is 1 by 1 is 1, so 1 plus 1 by 10. Vn by 1 is Vn, and this is minus V by 10 going on the other side, so it becomes V by 10. Okay, just we have taken Va common. Look, here what you can write, Vb is equals to Va. This is 0. So 0 minus Va is equals to 0 minus VA, acha, divided by 1 is also there, equals to VA minus V0 divided by 10. This you imagine VB is equals to VA. So VA minus V0 by 10. So we can take VA common. So VA, if you take common, we have 1 plus 1 by 10 is equals to V0 by 10. It means we get the value of VA to be 11 by 10. So V0 by 11. Okay, let's say this is equation number 2. So we are getting two equations. VA is equals to V0 by 11 and this. Now finally let's apply the KCL at C point also. So whatever value you are getting, just save it. Finally applying KCL at node C. Okay, what is VC? What is the voltage at C? You see, this is again, you can imagine it. This is a non-inverting input, it is grounded, inverting input with some feedback. So this 0 volt will be reflected here, right? So the voltage of C will be 0 volt, right? Because of the virtual concept, virtual ground concept. Now look at it. Here the voltage is 0 volt. Now if you apply KCL here, so V0, here the voltage is V0, so V0 minus 0 by 10 will be equals to 0 minus this V divided by 1 microfarad. Okay, so 1 microfarad, so we have to put equivalent impedance. So let's say the equivalent impedance is XC. So XC, we can treat it like a resistance, right? We can write V0 minus 0 divided by 10 is equals to 0 minus V by XC, where XC is equals to 1 upon J omega C, where C is your 1 microfarad. So for the timing, let's keep XC as XC. So from this, we can get the value of V to be minus V0 by 10 times XC. Let's call this equation as equation number 3. 1, 2, 3. Now let's put the value of V. Okay, we have got two equations, 2 and 3. Let's put these values into equation 1. Substituting equations 2 and 3, the values from equations 2 and 3 into equation 1, you get, what do you get? Look, what was there? VA 11 by 10, VA is equals to VN by, okay, let's just copy. (11 by 10) VA is equals to V in plus V by 10. So 11 by 10 VA is V0 by 11. This is equals to V in plus V by 10. V by 10, V is minus V naught by 10 XC into 1 by 10. Can I write it? And that gives you V naught by 10 is equals to V in minus V naught XC by 100. Our ultimate goal is to calculate the gain, that is V0 by V in. We can take a V0 common, 1 by 10 plus XC by 100 is equals to V in. That means V0 by V in is equals to 100 by 10 plus XC. So 100 by 10 plus XC is 1 by, okay, let's take 10 common and make it 10. 10 common, 10 get cancelled from both numerator and denominator, so we'll have to write 1 plus XC by 10. Okay, this is equals to, okay, it's just getting lengthy, but you can see it is very easy. 1 by J, next line please. Look here, 10 we have used for 10 kilo ohm. Okay, remember this one, I told you initially 10 we have used 10 kilo ohm, we have to give it back. Let's say, let's name it equation 4. What is the magnitude? Therefore the magnitude of the voltage. Look, the problem is simple. Actually they have made some additional circuitry in the problem to make it look like complicated, but it is actually very simple. C is 1 microfarad, 10 to the power minus 6, 10 kilo ohm. 10 kilo ohm is 10 to the power. One minus 1 by J is equals to minus J. Okay, and you see it is having omega in the denominator. Like 1 by 10 to the minus 6, 10 to the power 4, we can call it as omega C, where this omega C is 1 upon 10 to the power minus 6 into 10 to the power 4, that is 10 to the power 2 is the cutoff frequency, angular. Now we have to decide whether it is a low pass filter or a high pass filter. Okay, now you just notice one thing. As omega tends to 0, what is the value of AV? Omega tends to 0 means 1 by infinity, 1 by 0 is infinity, 1 something by infinity is 0, so AV is turning to 0. Let's say this is omega. Okay. Now when omega tending to infinity, means for higher frequencies, this A V approximately 10, you can say, or if you get more confusion, you can just like 10 by root over 1 plus omega c by omega. You can write it. So when omega tending to 0, AB tending to 0, and omega is much when omega is tending to infinity, you are getting a non-zero value of 10. So is it not something like this? You can imagine that after this omega c. So what kind of filter you can say it is? Tell me, what is this filter? Hmm? High pass. Okay. So this is a high pass filter. It is only allowing higher frequency signals. So and we also need to calculate the frequency. Okay, now in the question, I think the high pass filter cutoff frequency. You know, we have got the cutoff frequency. The cutoff frequency. What is the cutoff frequency? F is equals to omega c by 2 pi, है ना? FC omega c by 2 pi. So omega c have got 10 square by 2 pi. So if you calculate how much value are you getting, 10 square by 2 pi, 100 by 2 pi, 15.92, approximately 15.92 means approximately 16 hertz, and hence we can write, therefore the given circuit is a high pass filter with a cutoff frequency of 16 hertz, that matches with option A. So this is the best problem we have done till now in this class. Okay, how too many pages I have kept? Tell me guys, wasn't it interesting? क्या ये interesting नहीं था? With this, we are at the end of this OPAMPS chapter, and on the next class, what we will discuss? Can you tell me what is the next topic we have in electronics? I think A by D, D by A convert. Achha, oh, Boolean algebra and Carnot map we have. Okay, the next topic is also very important. Carnot map is very important. We will learn Carnot map on the next class. Till then guys, thank you very much for joining this session. I hope you find this session useful. Have a great day. Bye bye. Take care. How are you enjoying the winter? Too cold. I'm not opening windows too much. Cold wind is coming. बाय बाय गाइस, चलो आज के कार्यक्रम यहीं पे समाप्त करते हैं।